Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an associate professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the first lecture of the third module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's lecture, we shall first derive the Galerkin weak form of Poisson equation of heat conduction in vector form, and subsequently we shall find the element level matrix equation system with the consideration of all types of boundary conditions that we address in a heat conduction problem. The boundary conditions that we have considered belong to the essential, natural, convective as well as radiative boundary conditions. In the fourth lecture of the second week, while we were discussing the radiative boundary condition in the first part of the boundary conditions, there were some erroneous expressions. Those expressions we have corrected in today's class. This fourth set of boundary condition, the radiative boundary condition, the right hand side expressions, they were incorrect. So we have corrected those expressions and we have rewritten these expressions here in this box. So I suggest the students to discard the previous boundary conditions that we have discussed and then to consider the correct boundary conditions for the radiation boundary condition which we are showing here within the box. Now we shall derive the weak form of the Poisson equation subject to 4 different types of boundary conditions. We shall use the Galerkin finite element formulation, and from the weak form we shall derive the element level matrix equation system as a compact form where all the boundary conditions will show their individual contributions to the element level matrix equation system if it is available, and then the load vector. All the boundary conditions, they do not contribute to the element level matrix equation system, but all of them certainly contribute to the element level load vector. So we just consider the Poisson equation in heat conduction in vector form, and then we consider all 4 types of boundary conditions, the essential, natural, convective and radiative boundary conditions. The Poisson equation of heat conduction in vector form is given by k del square T plus Q equals to 0 on omega. Now we consider 4 types of boundary conditions. The boundary conditions are as follows: EBC T equals to G on gamma G. Then we write the NBC minus K n cap dot del T equals to minus K del T del N equals to Q0 on gamma Neumann. The CBC or convective boundary condition minus K del T del N equals to H into T minus T infinity, and on gamma C, and finally the radiative boundary condition RBC minus K del T del N equals to epsilon sigma T to the power 4 minus alpha Q bar double dot. So this represents the strong form of Poisson equation of heat conduction. Now, this is the domain, this is the omega, this is the boundary gamma. Now, the governing equation is k del square t plus q equals to 0. We show the individual components of the boundary here. This is omega. So this is gamma g, this is gamma h, this is gamma c, and finally this is gamma radiation, and our governing equation is k del square t plus q equals to 0. Now we shall derive the Galerkin weak form from the strong form, and then we shall use the Green-Gauss theorem to this purpose. The Galerkin weak form will be derived using the Green-Gauss theorem. The statement of method of weighted residual gives integration over omega w r d omega equals to 0. Since the integral form is valid for finite elements, we consider an arbitrary finite element and then we derive the weak form on that arbitrary finite element. From here, we write the integral form at the element level. So this is omega e w r d omega e equals to 0. So this was the domain. In this domain, we have considered one arbitrary element. So this domain is omega e and its boundary is gamma e. Now, over this element, this integral form is valid, which we write as integral over omega e w into k del square t plus q d omega e equals to 0. We simplify it as integration over omega e w, k is outside by taking k as constant, w del square t d omega e. We also take the heat source term as constant. It gives us q outside, integration over omega e w d omega e equals to 0. Using the Green-Gauss theorem, we obtain, using the Green-Gauss theorem, we get minus k integration over omega e gradient of w dot gradient of t d omega e plus boundary integration over gamma e w into k del t del n d gamma e plus q integration over omega e w d omega e equals to 0. Now, this first portion, it is the bilinear term bw comma t, and the remaining portion, it gives us the linear term. So we split the bilinear and linear terms to get k integration over omega e gradient of w dot gradient of temperature d omega e equals to the q into integration over omega e w d omega e plus the boundary integral term, the heat flux term or the natural boundary condition term, gamma e w into k del t del n d gamma e. For Galerkin finite element formulation or GFEM, we select w equals to psi ie or weight function equals to shape function. Our trial solution, is given as trial solution TH equals to summation TJE psi JE, J is varying from 1 to NEN, plus summation of TBE psi BE, where B belongs to eta G. Now the boundary, it can be shown as composed of the four different contributions from essential boundary, natural boundary, convective boundary, and the radiative boundary. So here the boundary is decomposed into gamma G, gamma H, gamma C, and gamma R, and accordingly the boundary integral term, which comes as Wk del T del N d gamma E equals to integration of W k del T del N d gamma He along the boundary plus integration of the same term W k del T del N d gamma convective E gamma Ce convective part plus the radiative portion gamma Re W into k del T del N d gamma Re. Now substituting this portion into the weak form, we obtain, substituting this decomposition in the weak form, we obtain k into integration over omega E gradient of W dot gradient of T H into d omega E equals to Q into integration over omega E W d omega E plus integration over gamma He W k del T del N d gamma He plus integration over gamma convective E W into k del T del N d gamma convective E plus integration over gamma radiation E W into k del T del N d gamma radiation E. Now for GFEM, we substitute W equals to psi IE. Also substitute the trial solution to get K integration over omega E gradient of psi IE dot gradient of summation of TJE psi JE, J belongs to 1 to NEN, plus summation of TBE psi BE, B belongs to eta G d omega E equals to Q integration over omega E psi IE d omega E plus integration over gamma He psi IE into k del T del N d gamma He plus integration over gamma convective E psi IE k del T del N d gamma convective E plus integration over gamma radiation E psi IE k del T del N d gamma radiation E. So this can be further simplified as equals to k into summation over j equals to 1 to NEN integration over omega E gradient of psi ie dot gradient of psi je d omega e tje plus k into summation over b belongs to eta g integration over omega e gradient of psi ie dot gradient of psi be d omega e multiplied by tbe equals to integration over omega e psi ie into q d omega e plus integration along gamma Neumann e psi ie k del t del n d gamma he plus integration over gamma convective e psi ie k del t del n d gamma ce plus integration over gamma radiation e psi ie k del t del n d gamma radiation e. Now in the left hand side portion we have one contribution from the essential boundary which is a known quantity and which we shift to the right side. The left hand side now constitutes only of the conduction contribution. So this we write as k into summation over j equals to 1 to nen integration over omega e gradient of psi ie dot gradient of psi je d omega e into tje equals to q into integration over omega e psi ie d omega e minus k into summation over b belongs to eta g integration over omega e gradient of psi ie dot gradient of psi be d omega e multiplied by tbe. Next we have the contribution from the natural boundary condition. This is integration of gamma he psi ie k del t del n d gamma he. Now let us consider the contribution from the convective boundary condition. This can be found as integration over gamma convective e psi ie into convective heat transfer coefficient into T infinity minus T into d gamma convective E plus the radiative contribution. This comes as integration over gamma radiation E psi ie into alpha qr double dot minus epsilon sigma into T to the power 4 d gamma radiation E. This can be simplified as k into summation over j varying from 1 to nen integration over omega e gradient of psi ie dot gradient of psi je d omega e tje plus here in the convective term and in the radiative term we find that we have contribution from the unknown degree of freedom temperature. So this must be shifted to the left hand side and remaining terms should be retained in the right hand side. This gives us integration over gamma ce psi ie h into t d gamma ce plus integration over gamma radiation E psi ie into epsilon sigma T to the power 4 d gamma radiation E equals to q into integration over psi ie d omega e minus k into summation b belongs to eta g integration over omega e gradient of psi ie dot gradient of psi be d omega e tbe plus integration over psi ie over gamma he. This is the natural boundary condition part. K del T del N d gamma he plus integration over gamma ce psi ie h t infinity d gamma ce plus integration over gamma re psi ie alpha qr double dot d gamma re. So here we have separated the unknown and known terms in the left hand side and right hand side. Now the temperature appearing for the convective and radiative contributions, they should be written in terms of the trial solution without the essential boundary part. So here this is the CBC contribution. This is the RBC contribution for CBC and RBC contributions to the left hand side matrix. The trial solution will be excluding the essential boundary part. It is T equals to summation TJE psi JE, where J belongs to that particular boundary, gamma C or gamma R. Now we simplify further to get K into summation over J equals to 1 to NEN integration over omega e gradient of psi ie dot gradient of psi je d omega e plus the convective contribution. It comes as h into integration over gamma he psi ie summation of tje psi je d gamma he plus epsilon sigma integration of gamma radiation e psi ie into summation of tje psi je d gamma re. Here j belongs to gamma re. Here j belongs to gamma he equals to q into integration of psi ie d omega e minus k into summation over b belongs to eta g integration over omega e gradient of psi ie dot gradient of psi be d omega e tbe plus h t infinity integration over gamma convective e psi ie d gamma convective e plus integration over natural boundary psi ie into k del T del N into d gamma he plus integration over gamma radiation e psi ie into alpha qr double dot d gamma re. So we can simplify this portion as k into summation over j equals to 1 to nen gradient of psi ie dot gradient of psi je d omega e plus h into summation over j belongs to gamma he integration over gamma he psi ie psi je d gamma he into tje plus summation over j belongs to gamma re integration over gamma re psi ie. This will be having t to the power 4 psi ie psi je to the power 4 d gamma re into tje to the power 4 equals to q integration over omega e psi ie d omega e minus summation over kibe tbe where b belongs to eta g plus integration over gamma he psi ie k del t del n d gamma he plus ht infinity integration over gamma ce psi ie d gamma ce plus integration over gamma radiation e psi ie alpha q double dot d gamma r e. Now we introduce certain terminologies. Kije for conduction. This is k into integration over omega e gradient of psi ie dot gradient of psi je d omega e. Kije convection equals to h into integration over gamma he psi ie psi je d gamma he. Kije radiation equals to epsilon sigma into integration over gamma radiation e psi ie psi je to the power 4 d gamma re. And then the right hand side load vector, this is coming as fie equals to q into integration of psi ie d omega e over omega e minus summation over kibe tbe b belongs to eta g plus integration over gamma he psi ie k del t del n d gamma he plus ht infinity integration over gamma ce psi ie d gamma ce plus alpha qr double dot integration over gamma radiation e psi ie d gamma re. So now we have the individual components from the conduction term, the convection term and diffusion term. From here we can write the matrix form in the following manner. So small correction here. So this is for convective part. So this should be gamma c, this should be gamma c. Similarly for the next line, this should be gamma c, gamma c. Here also this should be gamma c. K conduction, this is T plus K convection, this is T plus K due to radiation, this is T to the power 4 equals to Fe due to the source term plus Fe due to the essential boundary condition part plus Fe due to the natural boundary condition part plus Fe due to the convective boundary condition part plus Fe due to the radiative boundary condition part. Now, in a given problem, all the boundary conditions will not act together in a given element. So, most of the boundary condition components, they will be absent. Considering the left hand side, the conduction contribution will always be present. So, the conduction matrix will always be present. This convection and radiation matrix will be present only for convection and radiation boundaries respectively. Okay, now the size of this element level matrix, they will be NEN by NEN. The vector is NEN by 1. Now, let us consider the example of the natural boundary condition. Explanation for NBC. Now, the NBC term was integration over gamma HE psi IE K del T del N d gamma HE. Now consider we have an one-dimensional bar. Its left and right boundaries, they are subject to NBC, where at the left boundary the boundary condition is Q0L, at the right boundary the boundary condition is Q0R. These two boundaries are denoted by the symbols x equals to 0 and x equals to 1. So we write it as minus k dt dx at x equals to 0 equals to Q0L. At the right boundary we write k dt dx at x equals to 1 equals to Q0R. Now, if we consider this boundary integral term, then we get integration of gamma HE psi IE into nx dt dx d gamma HE for one dimension. Now, for left boundary, nx will be minus 1. So, the integral is integration of gamma HE psi IE into minus k dt dx into d gamma HE. At the left boundary, minus k dt dx is given as Q0L integration of gamma HE psi IE into Q0L into d gamma HE. Now, Q0L is a constant quantity, it will come out. So, Q0L integration over gamma HE psi IE d gamma HE. Now, if you physically see the problem, whatever the heat flux has been assigned at the left boundary, this heat flux has been occupied entirely at the left boundary. So the node at the left boundary at which temperature is unknown, their entire heat flux is taken by the node itself. It means that this integrand
it must be equal to 1. So it means that this gives us the Q0L quantity. The integrand finally reduces to the entire heat flux for a bar. Now, similarly, if we consider the right boundary, it can be easily shown in a similar manner that the heat is added to the boundary as Q0R contribution. For the right boundary, integration over gamma HE psi IE. Now, at the right boundary, Nx equals to 1. So, we are getting psi IE into K dt dx d gamma HE. This becomes equals to Q0R. Similarly, we can consider the cases of convection and radiation. Here, we shall illustrate the case of convection for the one dimension case. So, consider the CBC. Now, for the same bar at the left boundary at x equals to 0, we have convective heat transfer coefficient H1 and free steam temperature T infinity 1. At the right boundary at x equals to 1, we have H2 and T infinity 2. Our boundary conditions are minus K dt dx equals to H1 into T infinity 1 minus T at x equals to 0. And at the right boundary, we have minus K dt dx at x equals to 1 equals to H2 into T at x equals to 1 minus T infinity 2. Now, let us go back to the boundary integral. The boundary integral was gamma CE psi IE K del T del N d gamma CE. Now, for one dimension, this expression reduces to gamma CE psi IE K into Nx dt dx d gamma CE. Now, for left boundary, Nx equals to minus 1, then this gives integration over gamma CE psi IE minus 1 K dt dx d gamma CE equals to integration over gamma CE psi IE, and minus K dt dx represents H1 into T infinity 1 minus T at x equals to 0 d gamma CE. Similarly, for the right boundary, Nx equals to 1, we get integration over gamma CE psi IE K Nx dt dx d gamma CE equals to integration over gamma CE psi IE into K dt dx. So our K dt dx is H2 into T infinity 2 minus T at x equals to 1 into d gamma CE. Now, combining this case and this case, we see that in general, the convective term, the convective integral over gamma CE psi IE del K del T del N d gamma CE equals to integration over gamma CE H into psi IE into T infinity minus T, where this T is a variable, we write it as T of x into d gamma CE. Similarly, so these are the expressions which we have used in the previous derivation. The final case is the case of radiative boundary condition. This also we can show in one dimension. So here, for the RBC in one dimension, let us consider the emissivity epsilon 1 at the left boundary. The absorptivity at the left boundary is alpha 1 and the heat received is QR double dot at the left boundary. The same quantities at the right boundary, they are epsilon 2, alpha 2, QR right double dot. Now we have the boundary conditions as minus k dt dx at x equals to 0 equals to alpha 1 QRL double dot minus epsilon 1 sigma into t at x equals to 0 to the power 4. At the right boundary, the same condition is altered to k dt dx at x equals to 1 equals to epsilon 2 sigma t at x equals to 1 to the power 4 minus alpha 2 QR right double dot. Now the boundary integral which we got for the radiative boundary condition contribution, this is integration over gamma RE psi IE k nx dt dx for one dimension at and d gamma RE at the left boundary nx equals to minus 1. This gives us integration over gamma RE psi IE minus k dt dx d gamma RE equals to integration over gamma RE psi IE. Now minus k dt dx for the left boundary, it is alpha 1 QRL double dot minus epsilon 1 sigma into Tx to the power 4 d gamma RE. For the right boundary, our nx equals to 1. This gives us integration over gamma RE psi IE k dt dx d gamma RE equals to integration over gamma RE psi IE. For the right boundary, this is alpha 2 QR double dot R minus epsilon 2 sigma Tx to the power 4 d gamma RE. So we see that we get equivalent expressions when we consider the left hand boundary and the right hand boundary. So we can generalize the radiative boundary contribution as integration over gamma RE psi IE k del T del N d gamma RE equals to integration over gamma RE psi IE alpha QR double dot minus epsilon sigma into T to the power 4 d gamma RE. So when we substitute these expressions into the weak form, we have to substitute the trial solution expression for the temperature for both the convective and the radiative boundary condition contributions, and by that we got our expressions for the left hand side matrix contributions and the remaining terms contributed to the right hand side load vector. So the matrix equation system which we get after discretization, it looks like KETE equals to FE or KIJE TJE equals to FIE, where this KIJE is taking the contributions from the conduction, convection as well as radiation, and the boundary conditions contribution along with contributions from the source term, they are coming into FIE. Now let us show some examples for one-dimensional problem, that how the matrices from
convection and radiation implementations they look like. Now let us illustrate some simple cases by showing the role of the boundary conditions in modifying the element level matrix and the right hand side load vector. So consider EBC at one boundary and NBC at the other boundary of a bar. So let us take one bar of 1 unit. Now at the left boundary we have specified EBC, at the right boundary we have specified NBC. So the value of NBC quantity is Q0R and EBC, the temperature is 100 degrees centigrade. So the governing equation is K d2t dx2 plus Q equals to 0. We can consider K equals to 1 watt per meter degree centigrade, Q equals to 1 watt per meter cube, T at x equals to 0, this is 100 degrees centigrade, and Q0R is given as 1 watt per meter square. So right boundary is x equals to 0, left boundary is x equals to 1. We can consider a single element for this case. So if we consider a single element, this is element 1, these are the local node numbers. So these are the local node numbers small a, or also the global node number capital A. If we construct the IEN array for this case, the IEN array looks like E, A, only one element, local nodes 1 and 2. So the global node numbers are 1 and 2. If we go for the ID array, our equation number is 0 at the left boundary and equation number is 1 at the right boundary. So this is the global equation number condition. Then we are getting the array as A versus ID of A. This gives us at A equals to 1, ID equals to 0, at A equals to 2, ID equals to 1. Now we construct the LM array. So LM array gives us LM AE equals to P. So from here we get E, A, I, N, E, E. E is 1, A 1, 2, I 1, 1. Element level equations 1, 2. So for the first node, local or global, equation number is 0. For the second node, the equation number is 1. Now our matrix equation system will be KPQ TQ equals to FP. So here, using the LM array, this KPQ, this is actually K11 T1 equals to FP. FP is F21 plus the contribution from the source term for the Laplace or Poisson equation. The contribution from the source term, it comes as delta x divided by 2. Here our delta x is 1 meter, the mesh size, and then we have the essential boundary condition portion, that is minus K IBE TBE. So this can be written as, here K11 is K221
Then we have T1, our source term is delta x by 2. Our natural boundary condition F21, it will come directly. So this is given as Q0R minus KIBE. So here we are writing the equation at local node 2. So here it comes as K211 T11. Now later we shall show that the element level matrix for the Laplacian equation, it is Ke equals to K by delta x minus K by delta x minus K by delta x, K by delta x. So for this matrix, the K21 term, it is minus K by delta x. So this is equals to delta x by 2 plus Q0R plus K by delta x T11. Now T11, this is given as 100 degrees centigrade equals to T0. So we can simplify this expression as, there was a small error here. So this is x equals to 0 and this is x equals to 1. K221 T1 equals to delta x by 2 plus Q0R plus K by delta x into T11. So our K221 is K by delta x into T1 equals to delta x by 2 plus Q0R plus K by delta x into T11. So from here we can find out that T1 has delta x whole square by 2k plus Q0R into delta x by k plus T11. So this comes as delta x is 1 whole square by 2 into 1. Q0R is also 1. Delta x is 1. K is 1. And T11 equals to 100 degrees centigrade. So this temperature comes as 101.5 degrees centigrade. So in lecture 5 of module 3, we shall show more illustrations for implementation of different kinds of boundary conditions. And then things will be clear about the implementation of convective, radiative boundary conditions. Now we conclude today's class. In today's class, we have shown the compact element level matrix equation system for Poisson equation of heat conduction. Heat conduction subject to EBC, CBC, RBC as well as NBC. The convective and radiative boundary conditions augment the element level coefficient matrix. For today's class, I suggest the students to follow the textbook by J.N. Reddy. Thank you very much
for attending today's class.